What's up? Hope you guys are coming along okay. We're doing Thevenin today, right? This is the theorem. This is the badass theorem of this course as far as I'm concerned. So let's jump into it. No need to mess around. So what we want to do here is that here's the conceptual picture. It's an easy picture. It's hard to implement, but it's an easy picture. The goal of Thevenin's theorem is to identify and separate a portion of a complex circuit. That means you identify a subcircuit, you identify a load, and you want to calculate something about the load. But the subcircuit is complicated. So what you end up doing here is that you separate the subcircuit, and then you apply Thevenin's theorem to get a Thevenin equivalent circuit. Then we take this, since it's the equivalent, we take this Thevenin circuit and we reattach it to the load. And when you compare the first circuit to this circuit, this is much easier to solve. That's the whole idea. And so the Thevenin rules that you're seeing here is that ultimately your goal here is to calculate the Thevenin voltage, which is known as the VOC, the open circuit voltage, the Thevenin resistance or Thevenin Norton resistance. And the process is always the same. Excuse me. Step one is always determine the open circuit voltage, which is the Thevenin voltage, with all sources activated. Step two is then to go determine the Thevenin resistance. Now, what you're going to find here is that there's two methods. Method one is really only about a conceptual one so that you can understand what it is that you're actually seeing. Because I think it's important that you try to understand physically to the best of your ability what you're actually doing, believe it or not. When you get to method two, this is the method that's going to be on quizzes and exams. If you do method one on quizzes and exams, and it's a 20-point problem, I might give you 5 or 6 points out of 20. So it's super, super important that it's method two. Method one is there to give you a conceptual understanding about what it is that you're doing. And so what I want to do here is that I want to do method one and method two to try to ground you into what that actually means. But in the end, when we get to dependent sources, which is what you're going to see from me on quizzes and exams, you want to go in and you want to do method two. And so here we go. I want to go and I want to apply this so that you can actually see what is going on. And so the way I'm going to do that here is that I'm going to look at a example circuit. So my example circuit here, I have an 18-volt source with a series of resistors with the load. So what am I going to do? I'm going to remove the load, right? And my whole goal is to take this subcircuit now and replace it. I want to replace it with a Thevenin equivalent. My whole goal is to calculate the Thevenin equivalent like this. That's what I want to do. So I'm going to call this point AB, AB. And so if that's the case here, then I'm going to go to step one here. Okay, so step one is that you want to determine VOC, which is the same as the Thevenin voltage. And then step two, we want to go determine RTH using two methods. So what are the two methods here? Well, method one essentially says deactivate. You can only do this. Method one is only with independent sources. And what this tells you here is it says deactivate all sources and calculate our Thevenin at the open. Method two, you have independent and dependent sources. What it says here is that you place a short at AB and calculate I short circuit. Once you have that, then RTH is VOC divided by I short circuit. Those are the two methods that I want to do. So I'm going to take my circuit. I'm going to run with it. Here I go. Right? So here I go. Step one. So the first thing that I'm going to do here is that I want to determine VOC, which is the same as VTH. So when you're looking at this circuit here, what you're seeing here is that VOC is always calculated the same way no matter what. So here's my circuit. And what I want to do here is that I want to come in and I want to, let me put in my values.
And I'm going to get a stimulus check, so I'm going to be fine for a while.
And my job here is to go calculate this open circuit voltage right here. One of the hardest things to do in this course here, believe it or not, is eventually go in and figure out which method to use. So one challenge is figuring out what method to use to determine VOC. It really is. And so what my job is, I tell you what 99% of you are going to do. You know what you're going to do? You're going to go in and use node. Why? If you got a hammer, everything looks like a goddamn nail. So what I'm going to do here is that I'm going to try to change how you look. There's lots of ways to do this. So I am not going to use node. Not the way you're going to do it, but here, let me show you how I would probably do this thing. So the first thing that I would note here, I think I am going to use node actually, because I think that's going to be the fastest way. And so the first thing that I do here is that I go in here and I put in ground. So that means I have my ground node right here. Now that I have my ground set, you could see here is that if I come in here, one of the things that you're really looking at here is that you're seeing that this guy, this node right here, has to be what? VOC. Right? B is the ground. I'm going to make that VOC. So then you could see here is that I know that this node right here has to be 18 volts. And so what you're seeing here is that I have a second node, which is right here. So when I do my counting here, what I'm seeing here is that I have what? I have 3 nodes minus 1 source gives me 2 nodes to solve. I have a regular node in VOC, and then I have to label this other one. I don't know. Let's call this node, how about, I don't know, V1? It doesn't matter what I call it. Actually, let's not use 1. Let's use some unknown variable x. So now I got node Vx here. So if I look at that, my VOC, I don't have to write a solver for it because VOC is one of the nodes. So let's go do that. So then I'm going to focus on node VOC. So what do I have? I have 2 resistors connected. So I'm going to go 112 plus 110 VOC. I see that I have 2 mutuals. So I'm going to get, here, let me move this down a little bit. I'm going to do that. So then I'm going to get, I have 1/10 with Vx, and I have an 18 with the 12. Now note, I'm going to get minus 18. So what am I going to do? When I bring it to the other side, I'm then going to get 18 over 12. And then I have my second node, which is Vx, and I see that there's 3 resistors. So I'm going to get what? I'm going to get 6, 3, 10. There's my Vx. Now, note one of these is connected to VOC, so note that that's the 10. So I'm going to get minus 10 VOC. And then I have the 6 connected to the 18. That would give me negative 18 over 6. But when I take it to the other side, it's going to be positive 18 over 6. So what you're seeing here is that I now have 2 node equations. So what am I going to do? I'm going to get my solution. Since we've already practiced this with VOC here, VOC in this case, I end up getting 12 volts. So now I have VOC equal to 12 volts. So I'm going to go to the next step now. I'm going to go to step 2. Now I want to determine RTH. So what am I going to do? I'm going to use method 1. And this method 1 is only valid for independent sources. Okay, only valid for independent sources. So what am I going to do here? I'm going to take my circuit here. Okay, I'm going to bring it down into here. And what I do here is that I do the following thing here. What I'm going to do here is that the first thing that I'm going to do, I'm going to move it actually a little bit over here. The first thing that I have to do here is that I have to deactivate the sources. So in this case here, that means I replace the 18 volt with a short. So that means I'm literally going to come in here and I got to replace this guy with the short here. So I'm going to come in here and I'm going to take out that 18 volt here, and I'm literally putting a short between right here. So what does this mean when you have a short there? So from the viewpoint, okay, so what we're doing here is that we're actually looking inside the open AB right here. And you could imagine that you're a little observer right here, right? You're the observer looking into this circuit here. And then the question that we're asking when we do this is, what kind of resistance does this observer slash load experience by being at the open? In other words, what effective resistance does the load feel? And the effective resistance that the load feels is what we call the Thevenin resistance. So when you open it up like this, you are effectively seeing the effective resistance. So if you were to go and calculate this thing, right? So now to calculate this effective resistance, what we do here is that we do the following thing. We come in here, we paste our circuit again, and you imagine that you have an ammeter. So in other words, you come in with your ammeter here, and what you do here is that you connect the probe here, and you connect the probe there. And what it really does here, this is a white lie, but we're among friends anyways, is that the current comes out of the meter and then follow the path of the current. You could see here that the current splits here and here, and then it's coming here, and you could see what it's actually doing as it's going along the path here. So you're taking the effective resistance that the load sees, or what the ammeter reads. And so what am I going to do? I'm going to follow the current. So we calculate the effective resistance using resistor reduction. Okay, and maybe a good thing to do here is that if you're getting caught up on that, is draw in nodes, right? You could see, for example, there's this node, and then there's this node. So you could see that the 6 and the 3 are in parallel. And if you draw in this other node right here, you could see that the 10 is in series with the 6 and the 3, and then it's all parallel to the 12. So if I look at this thing, I could then come in and just say, what is the effective Thevenin resistance at this opening? And what you actually see here is that you see that you have 10 parallel to 6 and 3. And then this whole thing is in parallel with the 12 ohm resistor. So if this is the case, then we could then go write out the resistance of parallel resistors here. So it's got to be what? It's got to be 12 parallel to 10 plus 6 parallel to 3 divided by 12 plus 10 plus 6 parallel to 3. And if you compute this, you get 6 ohms for RTH. So using this technique, I'm using resistor reduction with independent sources that I could set to 0 so that I get the effective resistance that the load would see at that location right there. That is method 1. Now, when you're looking at that method, what you're seeing here is that you're really seeing this thing here. We now have this circuit here, right? We have this circuit right over here. And what you're seeing here is that now, if I come in here and I apply Thevenin's theorem, the equivalent circuit is this. I come in, I'm going to paste this guy in here. And what I'm seeing here is that now I have values, right? This is 6, 12, 3, 10. And what I'm doing here is that I'm saying that I come in here and I calculate VTH. So what's VTH? Well, we calculated that already, and we saw that that was 12 volts. And we just calculated RTH, and RTH was 6 ohms. So that means I now have the Thevenin equivalent subcircuit of this circuit on the left. And you got to agree that this is much easier to deal with, right? That's a circuit you could take home to your mama and say, look, Mom, this is much easier than that one. Okay, so now let's go to the next method here. This is the one you want to pay attention to.
Isn't RTH 4?
Was it 4?
I think, because
I
6
don't know.
parallel 3 is 2.
What did I write? I wrote 6.
6 parallel 3 is 2. 2 plus 10 is 12. 12 parallel 12 would be 4, right?
6.
It'd be 6.
Half of 12.
Oh, but 12 is half of 12, right?
Yeah, but 12 parallel to 12 is.
Yeah, my fuck up.
Okay. So then if I look at this thing here, then what I'm going to do here is that now I'm going to go after method 2. This is you apply this to dependent and independent sources. And so to get RTH, where now it's VOC divided by I short circuit here. So what I'm going to do here is that here's my circuit now, right? Here's my original circuit. So what you do here is that in method 2 is that you keep all sources active. So that means I do not short out. I do not short out that voltage source. So what you do now is that look at the sign convention. If you don't follow the sign convention, I'll take a point off on the quiz or the exam. That current goes where? I place a short, so we keep all sources active, and place a short at point AB. And so remember our polarity. Polarity is A is positive, B is negative. So that means this current is supposed to be moving from A to B. That's my short. So my job now is to go calculate what this short circuit current is here. Okay? So how would you calculate this thing? How would you calculate I short circuit? Well, I short circuit, I would say that 99% of you are going to do what? You're going to do mesh. Why are you going to do mesh here? You're going to do mesh because you see 3 loops. Therefore, you get 3 equations and unknowns, and you're off and running with it, right? Because that's the easiest thing to do. When I look at this thing, I know that there's really one node, though. If you look at the sky right here, my job is to actually give you alternatives. Look at my node for the ground. I have 0 volts there. I have 18 volts here. And you could see that there's really one node. So if there's one node, I could then come in and I could define that node. Let's call it VZ, since we called the other one VX. And what you're seeing here is that if I use node, I have one node, but I got to get that I short circuit. And I'm going to say that this node right here, at this point here, I think I'm going to call this node at point A, right? I want to focus on that point A. And I have one node to solve for. And I will apply KCL at node A. And so when I look at node A, if I calculate what node VZ is, then you could see here that the current is going to be what? I got the current of the 10. I got the current of the 12. And you could see that KCL then says that 10 plus 12 gives me I short circuit. So let's go do that. So here I go. I'm going to go look at node VZ. So I have one node. So here I go. So I got 1/6 plus 1/3, 1/10 VZ. Look at that. 3 and 10 are on the ground. Nothing's there. And then I have what? 1/6 times 18. I pull it to the other side, I get this. Dude, that can't get nicer than that, can it? So then if you calculate that thing, you're going to see here that you're going to get VZ equal to 5 volts. By the way, I could have done series and parallel, but it was just easier in this case to just write a node equation. And so now that I got that, now I'm going to apply KCL. So I'm going to apply KCL to get I short circuit. So if I look at node A, you're seeing here that I have I10 plus I12 equals I short circuit. So what's I10? You could see that I10 is going to be VZ minus 0 over 10, and then I12 is going to be 18 minus 0 over 12. So then, of course, if I just plug in my numbers, you're going to see here that this is going to be 5 over 10, and then I'm going to get 18 over 12, which is not, I was hoping to give a simpler answer, but this is 3 over 2, but clearly that's a half plus 1, so I get 2 amps, and so therefore I have my I short circuit. So my I short circuit is 2 amps. So now, what does Thevenin's theorem says here? So Thevenin's theorem claims that RTH for method 2 is VOC divided by I short circuit. but we already agreed that the voltage for VOC was 12 volts divided by 2 amps, and look what I get, 6 ohms again. So each method is giving me exactly the same resistance. So in summary, what am I seeing here? That the first thing that I know is VOC is the effective voltage seen by the load. So if I remove the load AB and I'm looking at AB, before I put that element in there, as I'm just about to stick it in there, what does it do? It sees that effective voltage. And in this case, that effective voltage was what? 12 volts. So I short circuit is what? The effective current seen by the load. So right before I take out the short to put the load in, what is that element going to see? In this case, it's going to be 2 amps. And if I look at the effective resistance, if I ignored everything and I just said, what is that load going to see at that moment? In this case, we see that that is that. And you could see that all of these guys are connected. So what do we call this? VTH. What do we call this? This is the Norton current or the I short circuit. What do we call this RTH also? The Norton resistance. So language-wise, it looks like that here. Okay, here we go. So my job here is to just train you, right? Get you to see all of these techniques. Okay, here we go. Let's do example 4.3. And what we're going to do here is that we're going to look at this thing and just keep practicing this process here. So here we go. So I'm going to do both methods, method 1 and 2. Okay, so here we go. So the first thing I'm going to do here is that I got to do what? Remove the load. So if I remove the load, then I'm going to have the circuit that reads 9 Okay, so that's my circuit right there. So this is what I want to convert into a Thevenin equivalent using 2 different techniques here. Now, before we do this, one of the very first things that I should really be thinking about is that before I attack any circuit, the first thing that I would want to do here is that I would want to simplify this circuit as much as possible. And one of the things that you're seeing here is that I can use source transformations. Okay. So what I'm going to do here is that before any calculations, simplify the subcircuit using source transformations. And remember, if you find that the source transformations are too much, don't do them. Okay, so the first thing that I'm going to note here is that check this guy out right here. I have a source in series. So if I have a voltage source in series with the resistor, I could do a current to parallel resistor transformation. And so look what I'm going to do. If I do this, look how the current flow is going to go now. This is going to give me what? If I look at that source transformation, I'm going to get a 9. And then I'm going to have a current source going which direction? Up. And that guy's got to be 8/9 amps. And then I'm seeing my 2. So right away, you're going to see that we're going to do that. And then I got this guy. And of course, I got the other guys right here. And then I'm going to continue to simplify this thing, right? I'm going to continue to simplify this thing. And if I continue to simplify, what you're going to see here is that the first thing that I'm going to note here is that this guy I can rewrite as one single source here. So I'm going to make a source here. So I'm going to try to change my sign here. So note that the 2 is bigger than the 8/9. So what I can do here is that I can continue to rewrite this, and I'm going to say, so now I have a current source going down, and that guy's got to be what? This guy has to be 2 minus 8/9, and that's got to be 18/9, which will give me 10/9 amps. And then I have one parallel resistor, which is now 9 ohms. And then this is a 6, this is a 10. And then I have this guy right here. This is A, this is B, and then this guy, I believe, is a 20, and this guy's a 4. Now the question is, could I do more transformations? And the answer is absolutely yes. But at some point, you got to ask yourself, is it worth doing more transformations? And yeah, I could continue, right? Because now I can get a voltage source. If I do another transformation right here, you could see that that's going to be what? I'm going to get a voltage source that's minus 10 like this. And I'm going to get 10/9 times that. This is going to give me a 10 volts. And then look, the 6 and the 9 can now be added. You know what? I'm going to move this down a little bit. So this will now be 6 plus 9, which is 15 ohms. And now I have a circuit that looks like this here. And so this is 20 volts, and this is 4 ohms, and that's A, B. And I'm going to just stop right there. Right? I could do another source transformation if I wanted to, but I think for me, that's more than enough because, come on, I effectively right now only have one loop. So here we go. So here's the first thing that you gotta be aware of. Now, that's the circuit that I'm going to deal with. So now I'm going to go to step 1. And I'm going to determine VOC. So let me go take this thing here. So when I look at this guy, I'm going to place this guy right here. And that's my circuit. So I'm going to take this 6 and 9, and I'm going to leave my 15 like this here. So the first thing that you want to worry about is that when you look at this, note that this is the direction of VOC right there. And what you should see immediately is that there's a warning. And the warning is this. Note the 20-volt source is in the open circuit. The big hint here is that use KVL to determine VOC. So what I'm going to do here is that I'm going to make some assumptions about the directions of what I want to do here. So what I'm looking at here is that look at the polarity of the 10-volt source. So if I'm going to have current, which direction is the current going to come? It's going to come in that direction. So that means the polarity of this guy must be like this here. So now what I'm going to do here is that I'm going to apply KVL around the open. So here I go. Here's my KVL. And it doesn't matter the direction that I take here. So my KVL then says I'm going to start at A. Look at that. So I'm going to get positive VOC. I'm going to hit positive V10. And then I'm coming. And then I'm going to hit positive 20. And then I get the voltage of the 4 ohm. But note, since this is an open circuit, there's no current across that. So that's got to be 0. So that 4 ohm resistor is a dead resistor here. So now what we want to do here is we want to go in and we want to sort of look at what VOC says. So VOC then says it's got to be equal to what? Just doing the algebra, it tells us it's got to be minus V10 minus 20. So if that's the case here, you could see here is that now this is the equation that determines VOC. So what this tells us here is that to solve for VOC, we focus on getting the voltage across the V10 here. Okay, so let's go do that. So my goal now is to solve for the voltage across the 10. Okay, so now we want to go in and solve for V10 ohm. Now, one of the things that you should notice here is that look at this circuit here. If you're looking at the circuit, you're seeing that that 20 volt does not contribute to 10 because we already accounted for that 20 volt. So I really have just a single loop. Right? I have a single loop. And you could see that this guy here is just a series circuit. This guy's going to give me the voltage across the 10. So what am I going to use? I'm going to use VDR. So the voltage across the 10 is then going to be 10, the sum over the 2 times 10 volts. And you could see here, that's going to be 100 divided by 25. I'm going to get 4 volts. So V10 is 4 volts. So now, this tells me here that then VOC is then minus V10 minus 20. So that's going to be minus 4 minus 20. So it's going to be minus 24 volts for VOC. So what is VOC? When I look at the circuit, it tells me the effective voltage that the load's going to see at point A, B. So now we got that. Okay. Now that we got the voltage, I now am going to go look at determining the Thevenin resistance. So now we're at step 2. We want to determine RTH. So let's go do that. Now, which circuit am I going to deal with? Do I want to deal with the original circuit? Hell no. We've already simplified it. Why go backwards? Our circuit is this circuit right here. We don't care about anything else. So we use our simplified circuit here, right? So I'm going to get rid of this. I'm going to get rid of this. All of this stuff here. This is my circuit. This is my effective circuit right here. Okay, this is my effective circuit. So we use the simplified, oops, not the original one, right? Because it's the same circuit. So here we go, method 1. So I deactivate all sources. So if I deactivate all sources, then what am I going to have? I'm going to have a short. I'm going to have a 15 ohm. I have a 10. And then I'm going to short like this. Look what happened to the 4 ohm. It's still there. The 4 ohm now shows up. I have a completely different circuit. So what am I going to do? I'm going to take my ammeter and I'm going to look at the resistance right in here. And this is what we're calling RTH. So if I look at RTH, you could see that 4 is in series with 15 and 10. So then RTH must be 4 plus 15, 10. And if you compute this number, right, you got 15, 10, that's, you got, what's it, 10 times 15 is 150 divided by 25. That's got to be 6, right? This has to be 6 ohms, so this should be a 10 ohm resistor. I'm pretty sure that's what it looks like. If I make a mistake, you got to keep me honest.
Shouldn't it be 5?
Oh, 5? No. 150
No.
divided by 25 has to be 6.
Yeah.
Okay, good. That's what I want to hear. Keep my ass on. Keep my ass honest here. So 10 ohms, right? 10 ohms. So I already know what the circuit looks like, but let's go to method 2. We want to calculate the same Thevenin resistance here. So now we're at method 2. Here you keep all sources active and place a short at AB. So here I go. So now I go back and I put in everything else, right? Here's my circuit. Now I'm going to go put that in there. So the big difference here is that now I come in and I put my short right there. Right? This is I short circuit. Look how I short circuit flows. It flows from where? It flows from A to B. That's the direction of this guy here. So now what I want to do here is that, what do I actually see here? Well, one, note that the 4 ohm resistor still exists here, right? It still exists. So I want that current. I want the current through the 4 ohm resistor here. So what's probably the best way? So the first thing that I would note here is that note, I'm going to pick the resistor. I really want the current of the 4 ohm resistor. And the first thing that I would note is that Note, the 20 volt and the 4 ohm are in series. Your goal here is probably to say, no, dude, just use mesh. And I'm saying, no, man, you got to think. Think your way through circuits. Don't look at everything as a goddamn nail. So look what I'm going to do. If they're in series, I'm going to switch the 20 and the 4. So I'm going to switch their locations. And if I switch their locations, look what I get. I get minus 10, or I get 10 volts, 15, and then I have the 4, and then I have my 20 volt source here. So I know that with the 4, I know that this is a direction of the current that I'm really looking for. That's I short circuit. But wait a minute, check this out. That's ground. I know this node. I know that node, right? I know that this is 20 volts. I know that this is negative 10 volts. I only have one node that I don't know. That node right there. So what should I call this guy? I don't know. How about Vx? So if I can get Vx, I then have I short circuit because it's just the current through the 4 ohm resistor. So what I'm going to do, I'm going to use node here. And if I do node, probably the easiest. So then I only have one node. So here I go. I go 15, 10, 4, Vx. And then I look at the mutuals. So let's be careful here. So note, 4 is connected to a constant. 15 is connected to a constant. So let's see if we could be clever here. So if I do 1 over 4 times 20, that's negative on the left. When I take it to the other side, it's going to be positive 1/4 times 20. And note, I have that minus there. So on the left side, it's minus 1/15 times minus 10 volts. So I get a minus and a minus, which is a plus. So when I take it to the other side, I'm going to get a negative 15, 10. So if I do that, and you solve for Vx, I'm going to get that Vx is then going to be 10.4 volts. I now know what that node voltage was. If I know what the node voltage is, what am I going to do? I'm going to apply Ohm's law now. Ohm's law across the 4 ohm. So then I say here that the current of the 4 ohm is then going to be the voltage of the 4 ohm divided by 4, but the voltage of the 4 ohm is then going to be what? Vx minus 20 divided by 4. And if I plug that in, you're going to find here that this guy then becomes 2.4 amps. But wait a minute, that's the same as I short circuit. Okay, that's I short circuit. So what does Thevenin's theorem say? That then RTH should be VOC over I short circuit. Now we already calculated VOC. It was what? Minus 24 volts here. Right? That's a negative voltage here. But look at the current. Ooh, man, dude, I made a mistake here. I would have taken points off of you. You should be taking points off of me. Look at this little baby here. That current is in the opposite direction. I forgot to put in the minus sign right there. Bad Carlos, right? Naughty Carlos. So then we come in here and it should be minus 2.4 amps and I'm getting positive 10 ohms, which is in RTH using method 2. How does that compare? What did we calculate the other one? Look at that, 10 ohms. Man, this is so sweet, it's making my teeth hurt. So now we come back and we're going to use the Thevenin's equivalent, right? When we have the Thevenin's equivalent, what I really mean here is that I have this circuit. I'm going to go up and get the original one, okay? Coming all the way up here. And so if I get the original circuit, it looks like this. I'm going to bring it all the way down here. So if I have the original one, it looks like this. That means that I can replace this circuit with VTH of negative 24 volts. Look at my polarity. And then I have a positive resistance of 10 ohms. These two circuits are identical, right? They are identical. I can't tell the difference between them. So now we have to go back in and we have to look at the load here. And I believe the load here was a 14 ohm resistor. So if it's a 14 ohm resistor, what does that mean here? So now we want to calculate the, what is it? Is it the load current? Yeah, we want to calculate the current. We want to calculate the load current of the 14 ohm resistor. So that means here that this circuit then reads minus 24 volts. And this is 10 ohms. And now I put in my load. And my load here is 14 ohms. And because this is A, this is B, we assume that the current should be going in which direction? The current should be going from A to B. This is I 14 ohms. But look at that voltage source. That voltage source is negative. So that's telling us that the current is actually going to go in the opposite direction. So this tells us here that from Ohm's law, that the current of the 14 ohm resistor is automatically going to have a negative sign because of the negative voltage here. And that's going to be what? 24 volts divided by 10 plus 14 ohms. And clearly that's negative 1 amp for the 14 ohm resistor. And you got to admit, even though Thevenin's is a pain in the ass to deal with, but once you get it into that Thevenin equivalent circuit, it's pretty nice what you actually solve in the end. Okay,
Alex?
so yes.
Quick question. When we plug in negative 24 volts, that's going to flip the polarity of the source, correct?
Yes.
And then wouldn't that make the current positive?
No. Because our definition of polarity is from A to B.
Right.
So we always define the current from A to B. That's our reference. So if I do get a negative polarity, that just tells us that the current is going from B to A. But if I get a positive value for the current, then it tells me that the current is going from A to B. So we need some reference, right? How do you know that you're moving either to the left or to the right of a coordinate system when you're at the origin? There's a sign.
Oh, I got it. Yeah.
Okay.
I was confused because I was thinking if we were to flip the voltage source, then the
But
current
by the
would be
way,
flowing.
I actually did flip the voltage source.
That's what
I did it sort of like verbally, but not so much, mathematically. Okay,
Thank you.
here we go. So now we're dealing with a dependent source here. Okay. And when you're dealing with a dependent source, this means the following thing here. If you apply method 1 to this circuit to get RTH, it is incorrect. You cannot do it to dependent sources. You can only use method 1 for independent sources. And so what we got to do here is that we can only apply method 2. Method 1 has you calculate VOC. So if you actually did VOC correctly on this, I'd give you all the points for the calculation of VOC. But that only gives you, so if you're talking about an exam problem, that probably, it depends on the circuit here. You're going to get maybe 7 to 8 points out of it. So you know what happens to the rest of the circuit? You lose it because you didn't do it right. Because you're going to calculate the wrong RTH, and therefore you start off with the wrong circuit. So you're solving a different circuit. Yeah, that doesn't work for me. So only method 2 here. So
Hey, Carlos.
yo,
So a question and sort of a follow-up from what Josh was asking about, A and B and the convention there. We might go the whole class without having this problem because, typically you sort of set it up in a way that looks like this. But what if, say, I was looking for the Thevenin equivalent resistance across the 6K ohm on the left side there? Which would be A, which would be B? Now, this circuit you have down here, well, either one. Yeah, how about the 9? Like, how about the 9 ohm? I want to establish the Thevenin equivalent resistance across the 9 ohm. Would I sort of like rotate the circuit like clockwise and say that B is, the lower, what's right now would be the upper left-hand corner? Or do I remove the 9 and put A, B in the same orientation that they are now without moving the circuit? So
yeah,
A would be
it turns out to be arbitrary.
It can't matter, is I guess my point.
It can't matter. What it really is a way of you and I communicating that that's the orientation that's being defined. With that orientation, you now know whether that current's going to be positive or negative. Otherwise, you could just tell me that the current's this value, but never tell me whether it's going up or down the resistor.
Okay.
So in general, you have to, just like you do in regular mechanics, you have to define your coordinate system. Here, you have to define your polarity so that everybody agrees that's what it means to be a positive current or a negative current.
And the convention is that A is considered a higher potential than B, and so the current flows from A.
Yeah, I actually had a really hard time when I was young because they always said, oh yeah, A is the lower, B is the higher. So I got that damn sign wrong every time because coming out of advanced E&M, that's the way they did it. B was the higher than the A, so I kept to that convention, which screwed me up. Okay, let's get started. Let's look at the circuit. So we want to get a Thevenin equivalent to this guy here. So the first thing that you note here is that you can simplify the circuit first. And the way I'm going to simplify it is that you could see that the 6K and the 2.5 milliamp source are in parallel. So I can get a resistor and a voltage out of that thing. And note that those guys are going to be in opposite directions. Why? Because we're assuming that that's the polarity of the current source. So when I create a voltage source from the from the current source, you're going to see that these two voltage sources are going to be opposing each other. So let's see if we could step a step here. So what we want to do here is that I'm going to convert this into a series and voltage source in series with this whole branch here. So the 6 and the 4 add, and then these two voltage sources, the one due to the current converted and the 2ix, are then going to be opposing each other. So if I simplify the circuit, so I'm going to simplify the original circuit via source transformations. Remember, I'm skipping steps here. So here I go. So my current source is going to have to be what? Look at that. 6 times 2.5. That's got to be 15. Look at the polarity of this thing. So the polarity of this guy has to be the opposite direction. And then this is going to be opposing that dependent source, which is 2ix. And then I'm going to add the 6 and the 4. So then what I'm seeing here is that I have this circuit that looks like this now. Right? Is that a 10? No, it's a 3K. And then what I have here is then I have a 1K. And that's my circuit. But then if I clean it up, I got to define a polarity here. And what helps me define the direction is actually this Ix. Look how the Ix is going down to 3K. So I'm kind of assuming that the current's going this way. Does that mean that Ix is positive? No. It just helps me to define that that's what it means. So then my real simplified circuit then looks like this here. So I'm going to write a dependent source. That's going to be 15 minus 2Ix. I have one resistor. And I have another. And look what I'm doing. I'm dropping all the Ks. And so now that's my circuit right here, where I have my Ix going right there. That's my circuit. So now, here I go. I'm going to start applying it now. Step 1. I want to determine VOC. So if I do that, the first thing that I see here is that that 1 ohm resistor in this calculation here, right? This is VOC. You could see that that guy's a dead resistor. It's dead. It doesn't mean anything. So now VOC, what we can see here is that just by looking at this thing, we see that VOC must be the voltage across the 3 ohm, but the 3 ohm has to be 3Ix. So here I go. Dude, there's a lot of ways to do this thing here. We could use VDR, we could use KVL. I think I prefer to use KVL. So I'm going to use KVL, which then tells me then I'm going to go in this direction here. And so therefore, it tells me what? That I have the voltage across the 10 volts plus the voltage across the 3 must be 15 minus 2Ix. So I'm just going to keep doing this here. So then there's only one current in the branch, so this has to be 10Ix plus 3Ix. And I got 15 minus 2Ix. So if I go and I calculate Ix, the value that I'm going to get for Ix, right? I got 15 and 15 on both sides, so I got to have 1. But wait a minute. I know these are kilo ohms, so I'm going to come in here and put my milliamp in here. I now have my Ix value. So then VOC is in 3IX, and I know that's a 3K times a 1 milli, so therefore this is 3 volts. So I now have VOC. I know my voltage. Now I got to go place the short here. So if I got to go place the short, I now want to go determine, oops, I want to go do step 2 now. I want to determine I short circuit. So here I go. So I'm going to go put in my original circuit. No, not my original, but my simplified circuit. There's my original circuit here. So what am I doing? Look what I'm putting. I'm putting what? My short across the open, and I want I short circuit. So the question is, how are you going to calculate I short circuit? Well, the first thing that you want to know here is that the previous IX of 1 milliamp is not valid for this circuit, right? This is a no-no. Why is that a no-no? Look how this circuit has a short, this guy has an open. They're two completely different circuits. So this IX is different than that IX right there. By the way, there's about 10% of you are going to go like, oh, I calculated IX. I'm going to go plug it into here. And I just want to thank you in advance, because that just reduces the algebra or the grading that I got to do. So I prefer that you not do that, because I want you to get your maximum points. But if you're going to do that, well, thank you. So here we go. So what I'm really seeing here is that the first thing I got to do here is that I got to get I short circuit, but I have that IX here, right? I have IX. So the one thing that I really got to get here is that we see here that to get I short circuit, we must determine IX first. Okay? We got to do that first here. So the question is this here. The first thing that I would note is that 3 and 1 are in parallel. Now you could do mesh, but my goal here is to show you different things here. And that the first thing that I would say here is that I would note here that 1 and 3 are in parallel. So that means that the voltage across the 3 and the voltage across the 1 must be the same. Okay? So that's one way to look at it. And so if I'm looking at this guy here, you could use VDR to get the voltage across the 3 ohm. But there's lots of ways to actually do this thing. The other thing that you can do here is that you can go in and you can start to look at this thing in terms of, I guess you could use, mesh. But the way I look at this thing here is that the first thing that I'm looking at is that I know that the voltage across the 3 ohm must be 3IX. And the question is, when I'm looking at this voltage here, we agree that if this is 1 and 3, then this voltage should be what? I can treat these guys as exactly the same. So then this has to be what? 3 parallel to 1. And then I'm going to get 10 plus 3 parallel to 1 times my voltage source, which will then be 15 minus 2ix. So what I did here, maybe I should have drawn this a little bit differently right away here, is that note that I'm really looking at this circuit right here. That this is 15 2ix. And then what I did here is that I squished these two resistors together. And this is the 10. This is the 3 parallel to 1. So now I have two resistors in series. But since they have the same voltage, this is also the voltage of 3 and it's also the voltage of 1. So what you're seeing here is that this is just a number. And note that I have one equation with Ix here. So if you do the algebra, you can get a solution to Ix. And in this case, you get a solution that reads that it's 1/3 of an amp. Of a milliamp, that is. So check this out. Look at this Ix. Look at that Ix. This is 1 milliamp. This is 1/3 milliamp. They're two different values. So now what I've done here is that I've used VDR to get the voltage and therefore the current Ix. So now that I have the current Ix, that means here that the voltage across the 3 ohm resistor, which is 3Ix, is then going to give me 3 volts. Maybe I should be more careful. It should be 3 times 1/3, which gives me 1 volt. But wait a minute, this is the voltage across the 1 ohm resistor because they're in parallel. And because they're in parallel, that tells me that then the voltage is related to the current, but this is I short circuit divided by 1. So this tells us here that I short circuit then should be 1 milliamp. So I now know what I short circuit is.
Is there supposed to be in the equation just above that where it says V3 ohms equals 3Ix? Is that supposed to be an equals after that? Because we're bringing in the 10.
Where are you bringing in the 10? Yeah, in the denominator.
Okay.
Right? Because I'm just using voltage divider rule.
Oh, okay, I got you.
So now that I have I short circuit, I could then go in and calculate what? With VOC, I could go calculate RTH. So now the Thevenin resistance is, it's going to be RTH, which is then going to be VOC, I short circuit, and then this voltage was what? 3 volts. This current is 1 milliamp, so therefore this has to be a 3K resistor. So if I go back and I look at my circuit, of course I'm going to look at my simplified circuit, right? We really want our simplified. Maybe we should go back to the original one. The original one's over here. I don't have the original one written out. Maybe I can do this instead. This is the original circuit. So if I go back to my original circuit, this is my original circuit right here. What is this original circuit? The Thevenin equivalent is that I have VTH equal to 3 volts. I have RTH, which is equal to 3K. And this is the equivalent Thevenin subcircuit. And you gotta admit, that's pretty nice. Right? That is a really nice circuit right there. And I guess that ends it for today, boys and girls. So, hey, thanks for showing up. I will see you guys. If you're in the Friday lab, I'll see you on Friday. By the way, I got a lot of emails for the delay of the homework. I'll delay it till tomorrow night, midnight. And I'll delay the quiz till tomorrow night, midnight too. Okay? Just to try to, I know that the material is tough. Okay? All right, man. I will talk to you guys later, okay? I'm
Have
off
a
to
good one,
get ready for 4A, man. Bye-bye.
Carlos.
Thanks, Carlos.
Yeah.